Recording is on. So as I was saying, what happens is when you see a polynomial and you see all the coefficients are not having the same sign, then you already know that there is a problem. If you see that one of the coefficients is missing, for instance, you have s cube plus s, so s square is missing in between, then also you can say that there is a problem. But the converse is not true. That is, when you have all the coefficients of the polynomial having the same sign, you cannot say that everything is hunky-dory, everything is good. So that is where we apply route. Now, when we applied route, we saw that what we look for is a sign change in the first column. If there is a sign change, then it indicates that we are going to have a root with a real positive part, which is bad. One of the questions that was raised immediately thereafter, I believe Manjunath was there, is what happens when during the process of evaluation of this route thing, we get one of our coefficients as equal to 0, because the first row coefficient is going to be used for finding out the next set of coefficients, and that first row coefficient appears in the denominator. So analyze this thing. I will now consider a polynomial like this. So I have already factored this out. I mean, I have started actually with the roots, and this is the polynomial that I get. So we already know what the roots are. So let us form the route array. So to form the route array, on the one side, I'll have start with s cube, the highest power, then s square, and then I'll leave some space because calculations are necessary from here onwards. So s cube, this is going to contribute 1, s square is going to contribute 2, then after s cube, first row we have s, which is going to contribute 1, and here again another 2 from s to the power 0. So we perform the route cross multiplication, and divide, and in the first row itself we are going to get a 0. So how do I tackle this? I can tackle this in two ways. When I do the next cross multiplication, what will I get? This is the problem that I will face. So to get rid of this, what will I do? So I'm not going to have any problems out here. But this 0, I'll replace by epsilon, and in that case, what am I going to get here? I'll be getting right. So this, when I use an epsilon, now I can consider the epsilon to be a small number. And you can verify that as well. That if I take epsilon as positive out here, say 0.001, so this ultimately will become so whether you take positive or negative is not going to matter. So our first column becomes one zero 1202. I'll come back to this page later. Let us consider another polynomial. Again, I'll start with known roots. Four 73, This will give me a polynomial like this. So the corresponding array will be so you'll have 1, 1, 2, s cube, um, sorry. Once again, I'll end up with a 0 here, which.
So for the S4, won't the second coefficient be 0? Okay.
I have changed. I think I made a mistake actually writing it out here. It's S4 plus S cube plus S square plus S plus 2. I missed out one term. Is there any updating problem today, or can you see everything clearly?
We can see, sir.
Okay. So here again, you'll put 0 is equal to epsilon, and you have epsilon minus 2 by epsilon, and you can again check that what will happen in this case if you take epsilon as small. So this sign is positive. You are going to get a positive here. You already have a positive here. If you take epsilon positive, then this is positive. If you take epsilon as positive, then this is negative, whereas this will again be positive. If you take them as negative, epsilon as negative, then what happens? Then this is negative. This will be, because this is negative, this will be positive, and this will be positive. So how many sign changes are there? Don't say that this is one sign change, because unless and until this kind of a sign change takes place in the second row from the top or in the last row, one sign change, means actually two, because you see that this is a positive to negative and positive. This is a very common mistake when you are doing these things initially. Negative, positive, so it's positive, negative, positive. Here, positive, negative, positive. So there are two sign changes. So if you have two sign changes, then the Routh criteria states that this means you are going to have two roots in the right hand plane. So this is pretty straightforward, and you can also see from the original polynomial itself, yes, what Routh has said is correct. You are going to have um, minus point that this and this, these are our dangerous roots. They are going to cause the response to blow up. Coming back to here, you see, here we don't see sign changes. It is so when we don't have that, then when you have a system which gives a polynomial with a 0 leading, then you are looking at a pair of roots on the imaginary axis, purely imaginary roots here. So this is what you do when you have a 0 only in the first column. This is the simplest example. This is one way of doing this. There is also another way. So this is what I will term as epsilon method, and now we will do the reciprocal. Will consider a polynomial with reciprocal roots. So how does this work? Once if you do that, then this is what you will end up with, only that it will be in terms of Z. So in this case, what is going to happen? Our original polynomial was so you are going to have 3, 6, 2, 5, 3, 1. So we'll have 3 into 3, 9, minus 30, by 5, that will be 21 by 5, this will be 1.4, and these you will be getting stuff like this. Now one thing that you can do out here is you can make this 1, you can make this 3. For a particular row you are permitted to do this cancellation. Okay, so that is permitted, but don't do it for the columns. So as you can see here, you will be capturing the sign changes through the reciprocal polynomial, and this works because what you are going to get is, I mean, like whatever roots were there earlier, you are going to get 1 by. So when you have a 1 by 0 case, then I mean, like the 1 by 0 that you are going to get, that will become 0 in this case. So unless you have infinity as a root, you are not going to face problems by this method. So this is a straightforward way of doing things, and as I told you, this is when you have a pair of imaginary roots, then you face such situations, but in most of mechanical systems we normally don't face situations like this that much, because one of the reasons is we have in control systems was to a large extent initially developed by electrical engineers and mathematicians, and our systems are highly inertial and capacitive, rather I would say highly inductive plus capacitive. So we have this inertia thing present and the spring thing present. Whereas if you look at electrical circuits, it's mostly RC or LC, something like that. So there is always a question of having S into S plus something. But our systems in general will have something of everything present. And that is why we also don't have, usually in mechanical systems, you won't come across systems with this business of double roots, which I showed in the last class, because they arise in electrical and electronic systems because of something called op amps, which you may have been taught. What op amps do is, I mean, like you apply a very high voltage, you get zero current almost. And when you put an op amp between two electrical circuits, then the transfer functions, two electrical systems, the transfer functions simply get multiplied. This cannot happen with a mechanical system because we don't really have that many true mechanical analog of an op amp, something which can do such a thing in a mechanical system. There will always be in between the connector itself of two systems will have some stiffness, some damping, or some inertia of its own, which will prevent these kind of doubling of roots from happening. So even if you connect two identical systems mechanically, the connector itself will ensure that you are not going to get this double root kind of thing. So these are situations you may not encounter that much when you are dealing with mechanical systems. So next, we have dealt with one bad situation where we have 1, 0. We'll deal with a better situation, a worst case, or rather the worst case scenario where we have a whole row of zeros. So let me just again start with a polynomial with the roots given to you. This makes things kind of easy to understand. But of course, in actual problems, you will be given the polynomial rather than in the factored form. Because if they are available in the factored form, there is no point in doing this Routh exercise at all. So here I will leave it to you. I'll expect some interaction from you people. So the first row is 1,
13.
13, 36. What is the next row?
0, 0.
Yeah. So I mean, like, this is a pretty obvious case. 0, 0, 0. All things are 0. So this trick of replacing something by epsilon is not going to work. You are going to have epsilon upon epsilon. And what is the characteristics? If you look, you can see that you are seeing roots, pair of pair of imaginary roots. This is where you get such a situation. You will also notice that we are getting a polynomial with coefficients missing, and the kind of polynomial that we are getting, it has S4, S square, S0. So this kind of polynomial is known as an even polynomial. You can also have an odd polynomial where, let us say that in place of S4 it was S5, in place of 13S square it was 13S cube, and we had 36S. So that would be an odd polynomial. So even and odd polynomials, they create this problem, which means when you are starting with a bigger polynomial and an even or an odd polynomial is a factor of that bigger polynomial, that is when you will see this zero happening. Actually, this Raoult process is a kind of factoring, not very straightforward, but it is a kind of factoring. So say after a couple of factorings you get this even or odd polynomial thing, then you will end up with this rows of zeros. So how do we manage this? Okay, we'll call this auxiliary polynomial PS. in this case, so we had yes, port 13 as well. So anyway, because we have encountered the 0 here right in the next row, so this will be the original polynomial. If you encounter this further down, then it will not be your original polynomial. So PS S cube plus 26s. So we'll have the new array, which will now look like this was 0, 0, 0, which will now replace with 4, 26, and 0 is as it is. And now if you do your calculations, now you won't face problems. So 4 into 13, 52, minus 26 will be 26 by 4, 6.5. Similarly, 1 into 0 minus 4 into 36 by 4 again will give me 36. And then some more complicated numbers out here. Sorry, this should be s to the power 0, yes. So, do we have sign changes? No sign changes. So, what can we conclude from here? Is it a stable system? Well, not exactly, because let us get back to when we formed this whole polynomial. what do we see out here? We are seeing that all the roots are on the imaginary axis. So naturally they won't be showing up as positive real part, but they are not desirable things. It means you give them the slightest knock and your whole system will start bouncing and keep on bouncing. Not a good thing. So when you have such a situation, all zeros and no sign change, then that means you are looking at roots on the imaginary axis. Now this situation that we have described is occurring right here at the beginning. Okay, we could have a case where, I mean, like this, all zeros is occurring. Let us say I am dealing with a 7th order polynomial and all these zeros is happening at S3, as in this case. So it means it is at the S4 level that there is a culprit polynomial, and that means there may be other roots that have been already factored out, but from this S4 level onwards, no sign change, but a row of 0 just below S4 indicates that we are going to have 4 roots on the imaginary axis. Any sign change above that S4 row, above and including the S4 row, they will be for due to the roots coming from the other factor of the bigger polynomial, that is this S7 order, let us say. So this can be factored into a S cube plus something something polynomial and another S4 plus something something polynomial, where this S4 polynomial is having this kind of a situation of double of repeated roots, or there are other possibilities also. I'll come to that. So this is gives us a handle also that Routh is not only going to tell you whether you are going to have instabilities or how many unstable roots are there. Routh can also tell you the distribution of these stable and unstable roots. That is, how many stable roots, how many unstable roots, and also how many possibly are there on the imaginary axis, and also other kinds. I'll just come to that. See, basically such roots are caused this problem of symmetrical pair of This is called quaternary roots. So this is another situation where the roots will be located symmetrically about the origin. So when you have factors, when you can factor your polynomial into stuff like this, that is when you are going to have this. So it means you are going to have terms like a square plus a square minus a square, or pair of complex conjugate roots, that is a quadratic, a square of a quadratic factor, which a quadratic which has imaginary roots and a square of that. So these are the 4 cases, and we can actually figure out from the Routh array how these how this business works. So I'll take a break now, and we will take up certain examples, or perhaps wait, let us just do an actual problem where the factors are not given, so to give you an idea of how things will look like, and then we'll take the break. So we have So when you go about forming the Routh table, it is going to look something like this.
Sir,
Yes?
can we apply the Routh table on individual factors of a polynomial? Like, let's say in this polynomial, let's say I already know s minus 2 and s minus 3 are the roots, just an example. And then the rest of the polynomial is some 4th degree polynomial. So if I
Yes.
have,
Yes,
can I
yes.
apply the Routh? Okay.
Yes, you can. Because why not? Because see, what you are saying is something like this. Let me add a page. Something like this, right? And this can happen. I mean, like, you have maybe plugged in some kind of a activated controller in your system, you know, your basic system. So
Yes.
somehow or other, this it just gets multiplied. Yeah. So that means
That means
see,
0 roots will never be a problem, right? As in, we can always like easily just avoid the
this is
0.
going to have a positive real part. So this is a headache. So let us say you have a s plus 1 and s plus 2. Nice stuff. Okay? So then you can always do the Routh for this, and then I mean, like, decide, okay, whether at least if this is my system, whether the thing is going to be stable or not. Because this you already know, and this is -1, -2. So this part you know that this is not going to create trouble as it is. So of course, when we apply a controller, actually what happens is things come through feedback. So it is just not a multiplicative effect. That is why we have a problem. This is a very rare case. I mean, like you can, maybe if you just have in a system, you are not using feedback control, but just feed forward kind of thing. So you are just putting in something in front and then trying to analyze what is going to happen. So yeah, so if you know, let us say this is your original system and you are having a system just plugged in front without any kind of feedback, and you wish to understand that whether the feedback, whether this plugging in is going to harm your stuff or not. So you will analyze this.
Okay, sir.
So
Okay, sir,
actually, see, this zero business is also a kind of like that. When I do this example, you'll find out that S4 so here I'll have 1, 6, 8. This will be 7, 42, 56. These are nice textbook problems, so you have this luxury of being able to cancel things out. In real life, things will come with decimal places and all that kind of stuff. And then you are going to land up with, I think, 1 into 6 minus 6 into 7 and sorry. And we are going to have form an auxiliary polynomial using this. As you can see, again we are getting an even polynomial. Most of the cases you will see an even polynomial happening. Plus so you are going to see a 12s and that is it. So this will become 4, this will become 12 and the 0 will remain as 0. And this again we can factor out 1, 3. So after that we can proceed and you will find that if you work out this example, it's 380 1/3 So basically see, out here we are having problems with this cube, no sign change. Okay, so I mean like we are probably looking at, if you are seeing no sign change, then likely we are seeing roots on the imaginary axis. We'll discuss this later. But so far as this S5 up to S4 is concerned, what does this mean? We are starting with an S5 polynomial and there is a stable root here, something with a real positive part which can be factored out, and we will be left with an even polynomial looking like this. So if we actually knew that particular root beforehand, if we could extract it beforehand, then we could have started our route with this itself and checked on the stability. So this is another answer to your question. And if there is a sign change, for instance, then we can already say, in this case there is no sign change, then we would have said that okay, there is one unstable root and other roots are lying on the imaginary axis, because from this part onwards there is no sign change. Suppose, let us say a different version of the problem, I had a sign change out here. So in that case, we would have to actually it would need a higher order polynomial to do that, but for this part of the polynomial we will have to analyze the roots, the nature of the root separately, and for this part there will be another analysis. So how to do that, I will be illustrating through some examples. After the break we will be reassembling at around maybe 3:10, 3:12. Okay?
Hello, sir.
Hello? Yeah.
Yes, sir. Please stop the recording and restart again after the break.
Okay.